Okay, thank you, everyone. So welcome to TigerGraph's Graph Guru webinar. Today's topic is part 2 of our 3-part series on Graph Data Science Library. And part 2 is going to focus on recent additions to the library. Some basic housekeeping items. So please make sure you're muted. You can ask a question at any time. There are 2 ways you can contact us in Zoom. If you have a question for the presenters, please use the Q&A. If you want to just sort of chat among yourselves, that's what the chat is for. But if you have a question for the presenters, and that we will, in general, hold the questions till the end, we may also decide to just type an answer during the presentation. So I'm Victor Lee. I'm Vice President of Machine Learning and AI at TigerGraph. I've been with TigerGraph for almost 7 years now. I started out as an electrical engineer and worked in chip design before switching to software and got really interested in graph databases and graph data mining. Joining me today is Wyatt Joyner, one of our solution architects. He is very much interested in graph theory and graph algorithms, has done a lot of the development for our graph algorithm library, and you say has some really cool hobbies, and has a much broader background than just computer science. So he'll be doing our demos today, and he's joining us from England. So our agenda for today is we're going to give a brief overview of the library. Some of you who saw part 1 have already seen this. This is just to get everyone up to speed. Then we're going to focus on the main topic for today. What's been added to the library recently? What are some of the new algorithms, the new categories, and their use cases? And then we will conclude with a demonstration of a couple of those algorithms, 3 of them. So, graph data science, what is that? Well, it's a pretty broad term. It's the use of analytical techniques to uncover insights from connected data. So the graph is the connected data. So sometimes just the process of connecting it reveals relationships that you weren't able to see before. And because now your entire data set is represented this way, it's very easy. And if you're using a native graph database, it's very efficient to traverse multiple levels of edges to both search breadth and depth and then start to apply analytical techniques. And in this case, algorithms, and applying those algorithms will help you compute things, compute results, and in which ultimately, if they're valuable, reveal insights that you otherwise would not have had. And just a couple of the use case in healthcare, we have customers who are using graph embedding algorithms and similarity algorithms to detect patients who have similar situations, their medical backgrounds, as well as perhaps their demographics, the treatments they've received so far, and matching them up is able to put people into groups so that if you see something is successful or not successful with one set of patients, we can find all the others in the same group to provide better, cheaper healthcare recommendations. So it's recommendations, but applied to the very important area of our health. Supply chain has been on everybody's mind. And, if trying to deal with disrupted networks, slower delivery than expected, shortages, unavailability of workers, these are all disruptions that we would not have expected to this scale. And the ability to recompute the optimal solutions quickly, so applying graph-based optimization techniques to find the best paths, to classify different situations. This is needed to be able to, take what we thought was a solution and come up with a different solution. So we can find economical and productive assembly and delivery processes. And then in financial areas, fraud detection is not just for the financial institutions, but also for the retailers. They're using embedding algorithms, community detection, and centrality algorithms to detect fraudsters and fraud activity. So TigerGraph's approach to graph data science is first you have to start with course, the database, having the right data platform. So we have a property graph database with massively parallel processing, which is scalable and distributed. So it can hold all your data, and because the parallel processing, it can compute results very quickly and efficiently. Then you need the right query language so that you can perform the actions that you want. It's easy to describe them, and then has the right performance. A lot of algorithms are inherently procedural, step by step, do this, do that. You need to be able to control flow. But because you're also doing statistical work, a lot of times having accumulation or aggregation is very important. And of course, for performance, you want that parallelism. So we developed our own query language, GSQL, which meets all those criteria. And then because you don't want to have to write a custom algorithm yourself for every situation, you want a library of things you can depend upon. So that's what we're here today to talk about, our graph algorithm library. And we'll do that later. And then you'd like to be able to run these algorithms in the database. So we've encountered customers who come with the expectation because they've talked with other vendors, they've looked at past products, and they figure, well, we'll store our data here, but when we want to run our analytics, we'll have to export it and run it over there. And that's just a waste of time and money. So for TigerGraph, the answer, again, having the right platform. If you have the right platform, you store the data in the database and you run your analytics right there. And so we've had our graph data science library for probably about 5 years now. It's fast, scalable. It the language it's written in, GSQL, enables you to translate the pseudocode you see in your research papers or in your college classes quite easily into GSQL because of this high level syntax, because of the procedural constructs like for loops and while loops and if else. You just copy it right in. And then the algorithms are open source, so it's available freely. You can look at how we did things and you can modify it. And we now have over 50 algorithms in several categories, and that's what we're going to focus on today. What are those categories? What are the new categories? And what are some of the new algorithms? So we've organized our library into 8 different categories now. 5 of them we've had since the beginning: shortest path, centrality, community detection, similarity. Well, classification we added 2 or 3 years ago. But more recently, just in the past 6 months or so, we've added 3 more: topological link prediction, graph embeddings, which is really getting into machine learning, and frequent pattern mining, which is often also considered unsupervised machine learning. So the new categories really lean into the area of machine learning. Shortest path is a classic. It's when you talk about what do you do with a graph? Well, you find paths. Centrality includes, the idea of there's actually a measure called what is the centroid of a graph? What's the diameter of a graph? What's the radius of a graph? These technical measures all have to do with following paths and figuring out what is near the quote edge of a graph and what's near the center of a graph. And so there are ways to measure centrality. Similarity, structural similarity. This is where people, sort of see in social networks. These two people are similar because they have similar types of relationships. These are all very common. And as more and more users are, more and more enterprises are trying to experiment with graphs, they're seeing new use cases. They're bringing use cases to us. We're doing our research. We're sharing everything that we learn and know, but we also have customers coming to us saying, I discovered a new use for this algorithm. And that's really exciting to us. And it's, I think, a great community of graph users is developing out there. So now let me get into today's topic. What is new? That's why you're here. So my point of reference is since last September. It was in October that we introduced our latest sort of version of the graph algorithm library when we renamed it the Graph Data Science Library, version 1.0, because we changed a little bit how it's organized. We improved that. And we also introduced like 20 new algorithms. So that includes new categories. So whole categories solving different types of problems, such as link prediction or a graph embedding. And we'll talk about graph embedding. There's sort of multiple ways to think about it and what it does for you. One thing that a data scientist would understand is if you said dimensionality reduction. There are also cases where we didn't establish a new category, but we just added more algorithms in that category. For example, centrality. We always have had betweenness centrality and closeness centrality. We now have about 3 additional measures of centrality. And why do you want more? Well, sometimes it's because you have different data, and different data requires, you need to adapt the algorithm slightly. Or sometimes, again, there are different ways. Let me give you a comparison for closeness centrality. Closeness is measured by what's the average distance to go from this node to every other node in the graph. And that average distance is sort of a measure of its closeness. Then there's betweenness. Betweenness is, does this vertex sit on the shortest path to get from A to B? So it's on the way. It's not the endpoint, it's on the way. And you get a high betweenness score if you are on that path of a lot of shortest paths from anywhere to anywhere. So they're measuring different things. They're both closeness, but they're different types of closeness. And again, different types of these measures, or sometimes a different way of computing the same answer is beneficial. And so just having, as we've talked from the beginning about why algorithms are like tools, why they're like building blocks. And it's why you can have your starter toolkit with just one screwdriver, one wrench, one hammer. But eventually, if you're gonna be a journeyman, you're gonna be a master craftsperson, you're gonna want dozens of different, not just different types of tools, but different sizes, different, how many different wrenches do you want? How many different screwdrivers do you want? They're all different, right? Different sizes, different heads, different weights. They perform different functions. So this is an overview of the library, but let me highlight what's new. So these shaded in yellow are the ones within existing categories that we added in last October or since then. A couple of them are even newer. So I'm saying since October till today, these are the new ones. And then these are new categories. So graph embeddings, topological link prediction, and frequent pattern mining are completely new categories. So if you add them up, there's about 20 new individual algorithms. And we didn't even list all the variations because to save space, we didn't list all the different variations of shortest path or of page rank. If you included all those variations, we'd have well over 50. So I'm going to talk about, I think, 2 new categories and about 3 several new algorithms in particular. So I'm going to go into some detail here now. So one of the new categories is topological link prediction. And link prediction is asking the question, should there be or will there be a connection between these 2 vertices, A and B, based on what we know about A and B? So as in our picture, here's A and B, and we're asking, I don't currently have this connection in the graph, but do I predict that there should be one? And why would I say should? Should is in 2 senses. It's the sense of the future. Like, for example, the Super Bowl will be in a couple weeks. Will Alex watch the Super Bowl? Or maybe you're talking about last year, but you don't have complete information. So it may turn out that Alex did watch last year's Super Bowl, but you just don't have the information recorded. So you're trying to predict what is the current state based on clues of what you know about A, what you know about B. And we have 5 different versions of topological link prediction algorithms. Now, these are pretty simple ones. Some of you are familiar with more sophisticated link prediction algorithms. I'm going to tell you what these are, and then we'll talk a little bit about those more sophisticated machine learning based link prediction algorithms. These are based on just taking simple statistical measures of what you see in the graph about A and B. So for example, this very simple one, the Atomic Adair measure. Just count how many shared links are there between A and B. Shared links, that means they have a connection between them. Or how many common neighbors? Like if we go back here, vertex 3 is a common neighbor of A and B. So is 4 is also a common neighbor. And there are different ways that you could work with those numbers. So here we count the number of neighbors, but here we take a product of them. Or so there are different ways of numerically dealing. But you see in all the cases, we're basically counting the neighbors and the neighbors that are in common. And then there are different ways of dealing with those numbers. And as I said, this is for prediction, or prediction is closely related to recommendation. You know, do you want to place a bet that Alex will watch the Super Bowl? That's why it becomes a recommendation. If you can know the future, then you can recommend a course of action. Now, one thing you notice is that these are asking about shared links. Now, remember, this is a person and this is an event, a Super Bowl. What does it mean to talk about their neighbors? Now, this idea, it works great if they are in fact the same type of thing. If this were just a social network and you're just talking about people and you say, who do you know in common or who do you work with in common? It makes a lot of sense to use these measures. If they're not the same type of thing, you may need to introduce one additional step, for example, and that's very common in collaborative filtering recommendation. What product do you recommend that I buy? So these are people and these are products. So you may need an extra step. So rather than comparing A directly with B, what you want to do is compare, in this case, compare person A, not with the Super Bowl itself, but with other persons you know have watched the Super Bowl. So we know person 3 has watched the Super Bowl, person 4 has watched the Super Bowl. Oh, and they're friends of or associates, whatever, of A. What does that mean? So taking the one thing about algorithms, again, in a library, they are standard. Like I said, the standard library is just going to compare A and B. What you may want to do is put that algorithm in context, and that's why I said these can be building blocks. What you want to do is compare A to other persons who have watched the Super Bowl. So you might compare A to 3 and compare A to 4. So this is, again, the category of topological link prediction. It is pretty straightforward, easy to compute. You can do a much better job of link prediction if you apply machine learning. Machine learning, what you're going to do is you are going to try to create a model to understand under what circumstances in general do links form. So if you can create a model which predicts in general when do links form, then you can say, okay, now tell me what the model predicts for A and B. So we're not going to go into that today. We've had other webinars that talk about machine learning, and we will have more in the future. That is my product area. So I'm sure I will be coming to you in the future to talk about that. The second new category is graph embeddings. And this is exciting, and this is really gets into machine learning. And a graph embedding transforms this graph structure. It looks at the connections, performs some global analysis, so to speak, and then it transforms it into the individual vertices. That's why I have these colors. So the the colors here match the colors over there. And then a vector. And that vector is called the embedding. So if I have 6 vertices here, I'm going to say I have 6 embeddings for those 6 vertices. So that vector represents the connectional information. It's not exact. It will not tell me, does, you know, this purple one and this yellow one, it will not directly tell me they're neighbors. What it will tell me is, do they play, it may say something about nearness, and it may say something about them sharing similar types of relationships. For example, this one, this orange one here and this yellowish one here, they both connect directly to this blue one with a edge in this direction from blue to them. In that sense, they have very high structural similarity. Once you get to blue, everything else looks the same. They only connect to blue, and they only connect with the arrow going from blue to them. That's about the highest similarity I could describe. So I would predict that they would have, I mean, I would say the embedding is for them are going to be very similar. Their embedding vectors are going to be similar. So that's what the embedding is. It takes this very complex multidimensional information and transforms it into a much more compact linear representation, which you can do these similarity analyses. So again, anytime similarity is involved, recommendation is usually an application. You can also group similar things together and perform classification. And the advantage is, again, it's more compact, so it gives you more scalability. It gives you that linear representation. So that linear representation allows you to then apply traditional machine learning techniques. So you get smaller, simpler, more compatible data. A lot of advantages to graph embedding. I'm not going to go into detail about, well, let me spend like 2 minutes to try to explain deep walk embedding. So we have this graph, and then we pick a random start vertex, actually for each of them. For each vertex, say C, it's C's turn, we do a random walk. So from C, we randomly pick a neighbor, which is A. Then we randomly pick another neighbor, which is B. Then randomly pick another neighbor, which is J. So we're getting this walk. And we pick a maximum length, in this case 16. So the walk is 16 long. Then we pick a window width, 2. So you look at on this, now you have this sequence, look at everything that's within 2 steps, either before or after C. So A and B came 2 after this C, but C reoccurs, and you look at what came after and before. And you count how many times each of these occurred. How many times did A occur within the window of C? A occurred 2 times within this 2-step interval. So A, we record the count here. You record the count for every possible vertex. This creates this count vector that we call a skipgram. You then create this, it's like a mini simplified neural network. This one hot vector that represents, this is supposed to represent C. If it's, I probably should have put it up here. It said A, B, C. But so it's only one is there. We then, do the traditional method of training this little mini neural network so that it tries to, so the output is just 2 stages long. So the output tries to match this skipgram. So this is the one hot input. The output is the skipgram. You train this so that these match. When they do, this hidden layer vector is your embedding vector. So that's called the deep walk embedding. And then there are 2 improvements. One's called node to Vect. And what that does is it adds sophistication to the walk. Rather than being completely random, it says there's a difference between going forward, going backward, or going to the side. And what's the difference between, what do we mean by forward or side? We talk about if we started in A and then went to C, so now we're at C. B was a neighbor of A, and it still is a neighbor of C. So any vertex that was a neighbor and then still is a neighbor is considered going sideways. So going to B would be a sideways move or breadth. Going back to A is, of course, going backwards. Going to any of these others is considered going forwards. So by paying attention to what direction you're going, you can get a better, more accurate embedding, an embedding that sort of models your graph better. But this is slower computationally. So most people found they actually want speed. So fast RP was invented, which is more scalable and faster. And rather than having to generate all the skip grams, which the set of skip grams or the size of the full graph, so it's n squared in size. This is using fast RP, you never need to have that n squared size. You pick a number d, which is much smaller than n, and the size here is only n by d. So again, it uses more randomization. The RP stands for random projection. Not quite as accurate, but it's a big improvement in speed and scalability. So talked about those two new areas, two new categories. One was the link prediction, and the other category was graph embeddings. Now I'm going to talk about some individual algorithms, maybe for about 5 to 10 more minutes, and then I'm going to hand it over to Wyatt to do some demonstrations. So I'm going to cover 3 categories: path-based algorithms. Breadth first search is so basic. The reason why we didn't include this originally is because we thought it was too basic, but we had some customers who asked for it, so we included it. A star it's a way to estimate what's the additional cost to finish out a path from where you are to get to your final destination. It's often used, it can be used when you've partially completed a journey and want to know what's the estimated cost to finish it. So think about you're reading a book, and you could estimate how long it will take you to read the book just based on the number of pages. And then, you read partway through the book. So then you have a real number for how long it actually took you to read that far. And then you can guess, again, how long it will take you to finish the book. We do the same thing for routing. And here the guess is usually based not by looking, you could look at the actual roads, and that would give you a very good guess. It's assuming what speed you'll be able to maintain on those roads. And even cruder guess is just to look at the geolocation, the latitude and longitude, and not even knowing the roads, just saying, I need to, if I could, again, go as the crow flies, it would be 1,500 miles. So if I could travel in a straight line, it would take this long. The A star is used when you have that way to estimate. MaxFlow is when you have a starting point and an ending point, and there's an idea that each edge has a capacity of how much flow it can handle, and you want to see what's the total amount of flow going through parallel paths, et cetera, that I can get from my starting point to the destination point. And Wyatt is going to show an example of that later. Didn't have any diagrams for that. I think I do have some diagrams. For community detection, Kmeans is a way to partition a graph into a set of clusters, and speaker-listener label propagation is also another way. The difference is here, partitioning, partitioning means you take the total number of items, in this case, the vertices of the graph, and chop it up into slices. So every vertex belongs to exactly one partition. In clustering or community detection is a little more general. It says, draw a circle, quote, circle, draw, assign vertices to a community. It may not necessarily include everybody. You might leave some out. You might just say, well, these people form a group. They're dense, they form a group. Those other people are kind of scattered. They don't really belong to any group. Speaker listener looks at the case where, hey, groups can actually overlap. So this is a little animated GIF I took from Wikipedia. And it's showing how Kmeans is an iterative algorithm. So what you do is you start with just a guess. First, you have to pick a K. K is how many partitions do I want? So it's not going to pick the quote, the optimal number of communities. You have to tell it how many communities you want. So if you want 3, you pick 3 random centroids. A centroid is if the red is one community, take the average their X and Y coordinates, and where would that average location be? That's the centroid. And so in some cases, it's the center, the most central location of a community at the given time, if you take this definition of a community. So the idea is you pick 3 random start locations, if K is 3. For those locations, compute what is the centroid. Now you have these new centroids. They now replace your original 3 starting points. Now do the same thing you just did. Now assign each vertex to its closest centroid. Now you have these new assignments, recompute the new centers. Again, now you have the new centers, repeat. So you keep adjusting membership and centroids, membership and centroids until it stabilizes. And this is just to illustrate the concept of overlapping communities. And you can imagine if these are discussion groups, you may participate in more than one discussion group. So you're going to belong to more than one community. And this is just sort of a more generalization or an upgrade of some of the more basic algorithms, which will say you can only belong to one community. And you can see how this has some real world value. And the last category I'm going to talk about are centrality algorithms. And here you're going to see there's a pretty close association with some of our existing older algorithms. Starting with degree. Degree, again, is one of those very basic ones where we didn't include it originally, but just for completeness, we did. In graph theory, the degree of a vertex is the count of how many connections or how many edges does it have. And you can separate between inward and outward connections if you want, or you can lump them together. So you can have in degree, out degree, total degree. And, it just means, is this a hub? Very general. Now, the next 3 are all variations of some of our older algorithms. Harmonic centrality is a variation of closeness centrality. It takes the same numbers that we would have used. We again, remember we talked about how far is it to get from this vertex to another vertex? How many hops is it? It just combines those individual measures, the individual distances, a little differently to come up with the answer. Eigenvector centrality is a variation of PageRank. You might actually say it's the other way around. PageRank is a variation of eigenvector centrality. Eigenvector, if you studied, again, linear algebra and matrix algebra, you probably have an idea of what that is. You might know exactly what it is. The thing is, not every vertex has an eigenvector solution. The thing that PageRank did, it did something very clever. The random jumping, the probability of jumping from anywhere to anywhere else, which they, Brin and Page and Brin, who did PageRank for Google 25 years ago, they had an application justification for that jumping. They said people don't always follow links. Sometimes you just go to a different page. You just type in a different URL. But for mathematical purposes, it actually guaranteed that they can actually have an answer. Eigenvector centrality is not guaranteed to have an answer. PageRank is guaranteed to have an answer. Article rank is another variation of PageRank. I won't go into exactly what the mathematical difference is. And this last one is a little bit different because all of these were computing scores. This one is not computing a score. This one is actually you could, if you wanted, put it into the community detection algorithm category, because what it's doing is it's finding a small set of vertices in a social network that maximize the spread of influence. So if these people are so well connected and so centrally located that if they were, quote, infected with something, it would spread throughout the graph very easily. That just is hitting a little bit too close to home these days, I guess, when I'm reading the news about all the people testing positive at the Olympics. So I'm going to switch over to Wyatt right now. I did have a couple slides to talk about what he's going to present, but rather than me talking about hierarchical Louvain and randomized maximal independent set, I will just let him show it to you. You'll be able to get a copy of these slides later. Obviously, I haven't gone over everything. You can read our documentation and go to our graph algorithm library on GitHub and take it away, Wyatt.
Hey there, everybody. All right. I think Victor introduced me as hailing from England, but so maybe you expected a British accent, but I'm actually just temporarily expatriated, so hence the accent. I will share my screen here. Give me 1 minute. Yeah. So I guess it's all right if we just hop into this live demo. Actually, maybe it'll be better if we look at the slides. I'm not sure. Victor, which way do you think we should go about this? Hop into the demo, or do you want me to give the high level on the slides? All right, sure. Sure.
Just narrate.
Yeah, yeah. So let's start with the Louvain algorithm. So Louvain, like many other graph clustering algorithms, is trying to optimize some type of clustering index. A clustering index is basically just a metric that dictates the quality of your cluster. Case, the modularity is the clustering index that it's trying to maximize. Modularity measures the proportion of intra-cluster density, so how many edges exist within an identified community, versus the inter-cluster density, so the number of edges that actually cross the boundaries of communities and exist outside communities. So it's trying to maximize that intra-cluster density. So this is my schema here. It's pretty simple. What's notable about this new hierarchical Louvain that we're implementing is that we're actually generating and embedding the results directly in the graph. So you can, once you execute a single iteration of Louvain and it generates aggregate nodes, which represent identified communities, you can actually pause, investigate those aggregate communities, see if you're comfortable with the results. If you want to, you can even re-execute that same iteration, or you can take those aggregate communities and then rerun Louvain over them, and then cluster the aggregate communities, and then look at the next result after that to see if you're happier with those results. Maybe the communities weren't the exact size that you were expecting, or there are a couple different disconnected nodes. So that's the benefit of this new version of Louvain, which embeds the results directly in the database. So here I have the node, which is our base vertex type. This could represent anything. So very creatively, I named it node. This is the relationship between the nodes called node edge. Note that it has an attribute called weight. If you're familiar with the concept of a weighted graph, weight can represent anything in this case, but typically it'll be like strength of connection or influence or something along those lines. And then importantly, we have this ag node, the aggregate node, which is important because this is where we are going to, this is the vertex type that we're going to use to embed the results. And importantly, we have this parent relationship. Note that it's a directed relationship where the source is the child and then the target is the parent. Note also that node edge that we saw earlier here can also exist to connect our aggregate vertices. So if you have two base vertices that are initially connected, but they get clustered into separate communities, that connection will ultimately be preserved in this node edge link that will exist between their parent aggregate nodes. So let me share. I actually ran this algorithm a couple of times just to generate some results because, well, first of all, I just wanted to validate it, but second of all, I thought it would be good to show you a quick example. I don't think this filter will apply anymore because I just changed it. So let's remove this filter. There we go. But let's select a quick example here. minor explosion of nodes. So for instance, let's start with this vertex here. This is just to show you some of the previous results from this algorithm. We can expand here. Let's expand out the parent. And we'll see here is its embedded parent here, this aggregate node. We can take this vertex. We can expand its parent. So we can actually see, we can see for this aggregate node here, these were all the nodes that were clustered. And then, well, not all of them. I note that it's only limited to 20 vertices at the moment. But then I also included this parent vertex here. And if we expand this again, once again, we see that this vertex has several children vertices, which are themselves aggregate nodes, because I ran Louvain a second time over those aggregate nodes. And this is its parent here. So hopefully this kind of gets across the idea that what we're doing is a hierarchical algorithm, and we iteratively run it on each set here. So first we ran it on the base vertices to cluster them. Then we ran it on these vertices, and I can expand these guys. Let's only expand towards the node vertex type. Let's expand these guys. So this little flurry of nodes here, these guys were all clustered together. And then they were all clustered in this cluster, and they were all clustered, this, and I presume its neighbors were also clustered under this cluster here. So that's basically the output that we're going to expect from this algorithm. I'm going to show you the code, which we can run it in this demo if we want. It takes a couple minutes to run, so if we're okay sitting around waiting for it to run, we can do that if we want. I just wanted to walk you through kind of what to expect in terms of the parameters and what this algorithm is capable of, or what this query is capable of. So this algorithm can actually support several different vertex types. In my schema, I obviously only have the base vertex type and the parent vertex type, but it would work for heterogeneous graphs as well. And one of the modifications that I'm going to be adding very soon to this is the ability to support multi-hop connections between vertices. So right now, the schema is just direct connections, so node directly connected to other node. I will soon modify this algorithm to actually support two-hop connections. So you can have a node connected to some intermediate vertex, which then would connect to another node. And that relationship can be treated as the relationship strength between those vertices. These other attributes here, like the ID attribute to expect, or the query key attribute, which I will explain in just a second, these are just to make the algorithm what we call schema free. So in case you haven't noticed from this discussion of a schema, TigerGraph is a schema first graph analytics engine. And in general, we like to keep our algorithms as agnostic as possible of the operative schema that you're using. So we include all these parameters so that even if, let's say, your expected ID attribute is not in fact ID, maybe it's name or something like that, it's actually fully parameterizable. So this is intended to work on most schemas within some constraints. The other thing that we're expecting here is a query key. So when you run this algorithm here, you supply, I like to run node. The ID attribute is what I expect. The parent edge type. Oh, sorry. This is sorry. This was actually the second algorithm that I wanted to show you, but the parameters are very similar. They mostly stand for the same thing. We have vertex type. You can also provide an edge type. The weight attribute is parameterizable. Here it's obviously just named weight, but you can name it whatever. And we still have these query keys, which I will explain now. So the way that this algorithm works when you run it is you provide the vertex types that you're interested in clustering. You provide the operative edge type that you're using, which I have brilliantly named node edge. And then all these other, these are parameterizable for reasons I've explained. And then we have the query key. So for the base vertex type, the query key is meant to be blank. But for the next query key, what you're effectively defining here is what do you want this invocation of Louvain to be labeled? So for instance, if we go back to the Explore graph and we look at these clusters that I've generated, you'll see query key is cluster 1. And for the next layer up, the query key was cluster 2. And the third layer up, the query key was cluster 3. I can label these invocations whatever I want. And the reason for this is that you can actually run this algorithm, you can run this Louvain clustering algorithms several times, even at the same hierarchy, the same level in the hierarchy. So if this is like the level 1 hierarchy, and the label and the query key is cluster 1, I can choose to run it again with just a different label, and it will generate different aggregate nodes. And this is pretty nice for several reasons. One, it allows multiple users on the system to be able to run this algorithm in parallel. It also allows you, it affords you the ability to go back and rerun certain iterations that maybe you weren't very happy with the clustering. Because Louvain, like many other clustering algorithms, is stochastic. So you get non-deterministic results when you run this algorithm. So if you're not too happy, you can choose to run it again, just provide a different query key, and you'll get different aggregate vertices. So once you run this algorithm, you can choose to apply the results. Maybe I'll just run this query because it runs a bit faster. So that's a bit easier to demonstrate for a demo. But once again, we have vertex type, all these parameterized things. And what this query will print out is the summary statistics of the algorithm. So it'll show us all the clusters that we've generated and the sizes of those communities. So the vertex type, the target vertex type here is aggregate node, because that's where I'm starting. The parent edge type that I expect is actually reverse parent. If you notice, this is a directional edge. And what I actually want is the edge going from parent to child. And the query key that I expect, let's start at, I believe I went out to cluster 4. It'll let me know immediately if that isn't the case. And the attribute is query key. The CID, which stands for community ID, is just the attribute that I would like to store the result on my base vertex type. And I can choose to clear the aggregate vertices as I traverse them. But for now, I'll just leave them in the graph. But let's run this algorithm. I may have to increase the runtime, because by default Graph Studio, no, okay, it actually ran pretty quickly. So here are all the generated communities, and these were the sizes of those communities. So we got some pretty large ones, we got some smaller ones. And an additional modification that I will be adding to this algorithm is the ability to have an expected maximum, or I guess a maximum size for your communities. So let's say you're really not interested in having a community that's as big as 60,000 vertices. You can choose to cap that, and then this algorithm will basically refuse to merge those vertices, and will opt for something that by modularity's perspective is suboptimal, but perhaps from your perspective gives you more appealing communities. So I hope this is all making sense so far. I guess we're looking to save questions for the end, so I'll just move on to the next algorithm, if that's okay. Let's look at maximal independent set next. So this algorithm, if you know what a maximal independent set is, then it's the random is the operative word here. What a maximal independent set is it's identifying a set of vertices such that none of them are connected to one another. And ideally, it is trying to maximize that set of vertices. Now, finding the largest independent set, the maximum independent set, is actually an unsolved problem and has been unsolved for a long time, and probably will be for a very long time, depending on your opinion on P versus NP. But needless to say, incredibly computationally complex. So we oftentimes rely on this algorithm, maximal independent set, which gives you, once again, a stochastic result. And it's just a heuristic to try to find a subset of vertices that are not connected to one another. So I can run this algorithm. I think this has a slightly different schema. Note this, I'm running this in a different TigerGraph database here. So our operative edge vertex type is node, or edge type is node edge. 100 iterations sounds okay to me. It's probably not going to run that long because this isn't a terribly huge graph. I can choose to write this to file if I want. And the print accumulator will decide whether or not I want to print out the results. And the reason why I picked a particularly small graph small is that I actually did want to be able to show you that I have all these vertices, and I can double click to expand them. And you'll note that it wasn't connected to any other vertices in my result set. So these are all independent vertices. This was a shared neighbor between them. So it came very close to not being a maximal independent set, but they just had a shared neighbor. So yeah, now I guess you might be wondering, what are some of the use cases for a maximal independent set algorithm? One of the use cases actually pertains directly to Louvain. So the way that Louvain works is iteratively, each vertex is deciding whether or not to merge with one of its neighbors. Now, if two adjacent vertices are both making that decision at the same time, then they could make conflicting decisions. They could decide to swap to each other's communities, because obviously it's not a very smart algorithm. These vertices don't know that they're swapping communities. Or one vertex would be swapping to another vertex's community on the assumption that the vertex was going to stay in that community, but it actually jumps ship and hops to another community. So you end up with these conflicts. So where maximal independent set comes in is that you find some big unconnected set of vertices like this, and then you let each of those vertices perform that computation in parallel, and then you're guaranteed not to have any conflicts. None of these vertices are going to swap communities because none of them are adjacent to one another. So maximal independent set is a great way to optimize the accuracy or the quality of clustering in algorithms like Louvain. It also has more general applications for anything that has to do with task assignment, where you don't want adjacent things, as it were, operating at the same time. So I hope that gives you some idea about maximal independent set. Oh, right, and randomized here. So we already have a maximized independent set, but it's a deterministic algorithm, meaning you're going to get the same result every single time. What randomization does here, hence this little random query, this function invocation here. What this does is it makes it stochastic. So if you weren't very happy with the previous result, you can run it again, and it will give you a different maximal independent set, or it probabilistically will give you a different maximal independent set. And that's useful for heuristic algorithms like this. The final algorithm that we want to go through is MaxFlow. So MaxFlow, once again, very simple schema here. We have a node, and we have, it's a transaction. This doesn't have to be a transaction. In fact, the most common use case for MaxFlow is in supply chain optimization. So if you have some bill of materials, or if you have some, if you're producing some components, and some of those, or let's say you have like a bunch of manufacturing plants, and you're deciding how to allocate resources to maximize production through these plants. And some plants produce materials that are used by other plants. But every plant can only support a particular capacity of materials at a given time. So you can't just overload a plant with some mass of materials. So what you're trying to do, oh, I apologize, I left, left the Teams open. With MaxFlow, what you're trying to do is maximize the logistic capacity of a network. Now, this is also useful in fraud detection. The basic use case in fraud detection is that given what's called the source of the network, and then what's called the sink of the network, and then a bunch of intermediate vertices in between them, you look at the flow of, if you're talking about like money laundering or that type of fraud, maybe these represent users in some type of transactional database. And you look at the transactions between them, you consider what the capacity of transactions could be between them, and then you see whether or not the network between the source and the sink looks like a suspicious pattern, or is suspiciously optimized. In other words, does it look like it was using some type of MaxFlow operation to maximize the throughput from the source to the sink? So I'm going to run this. Oh, I have to install this algorithm. This gives you a quick This is a quick lesson in TigerGraph. Most of our algorithms we can run in what's called interpreted mode. Interpreted means it just compiles it on the fly, but this is generally a bit slower. Well, not generally, it's almost certainly slower than installing the algorithm. Installing just means pre-compiling the algorithm from this high-level GSQL code to the lower-level C++ code that it ultimately compiles to. So let's run this algorithm here. So you have to know beforehand what your source and your sink vertices are going to be. I happen to know the IDs or the expected IDs of this data set beforehand. So I'm plugging those in. The expected node type, the expected edge type, which is transaction, and then the reverse edge type, which is just reverse transaction. The capacity attribute, which looking at the schema here, give me 1 second. There's the schema, here we go. Looking at the schema here, it's called capacity. And then the expected type, which in this case is a float. We don't usually go this far in genericizing our GSQL algorithms, but some of them do support like int, uint, float, double, whatever. Most times we just expect you to have a float, but some algorithms are more flexible than others. This one actually lets you have a custom data type there. The min flow threshold can be left alone for now. The printacume will leave on and display edges will leave on. We don't want to write to file, but this would be this is the default file path if you do want to write to file. And let's run this algorithm. So the reason why I picked a particularly small graph is because I wanted to have some type of explainable output here. So let's start at 9 because that was our source. And then 10 was our sink. And really quick, so this is the graphical output here. We also have the JSON output, which tells us that the sum of flow, that is the maximum flow that can go through this network, is 10. So that is given the capacities of these edges, what was the maximum flow that could go through here? And oh, unfortunately, it's not displaying the values here on these edges. Oh, darn. I need to tweak this a bit to get it to display those attributes correctly. But right here, it's pretty explainable what's going on. We're starting at 9, which is the source. We have 10, which is the sink. And then the flow is going through these transaction vertices to get to 10. And the algorithm tells us that the maximum flow allowed here is 10 units, whatever that unit may be. Maybe it's currencies, maybe it's raw materials, whatever it may be. Yeah,
thanks, Wyatt. We're right about an hour now. So
yeah,
pretty close to finishing up.
Yeah, no, absolutely. I think if there are any questions that want me to go into explaining a bit more about how these algorithms work, I can do that, but I think it makes sense to go to Q&A at this point.
If anybody out there had a question, please put it in the Q&A right now. But thank Wyatt for preparing these presentations. And we're available right now if you have questions. And again, you can do that through Zoom. Oops. Trying to go in present mode right here. And again, if our graph algorithm library is available open source on GitHub, you can also try TigerGraph Cloud for free, or if you prefer to download the product, there's a free version, and you can ask questions for free on join our community. We have a certification program, self-training for the graph algorithms. And in 3 weeks, I will be back to talk about improvements to the library itself, not the individual algorithms, but making it easier to run the algorithms, right? Rather, there were I expect to show you that they were actually built into the product rather than having to go to GitHub to get them. You will always be able to update the library by going to GitHub, but in 3 weeks, I'm planning to show you a new version of the product that integrates the library with our database. So I don't see any more questions. So again, I want to thank everyone for their time. We will get a link to the algorithm, excuse me, to the video and to the slides. And again, you can chat with us through the community at any time. So thank you so much from both of us.